Can you guys hear us now?
Oh.
Hey, Galen, I can see you. Can you hear us?
Yep, we can hear you.
Okay, great. Thank you. And can you see the presentation screen okay?
Yes, we can.
Okay, good. So we're going to get started here in a minute. And for those of you online, we're going to be sending the results out and your code and everything probably tomorrow morning, if not tonight. So if you can just bear along with us, you can see what the style of the graphs are and the distributions and things like that, but you probably need to sit down and look it over fairly carefully once you get your codes and that. So if you do have your data sitting beside you, as we go through the graphs, we're just going like analysis by analysis, so pH, TA, etc. If you have your number, your data beside you, you can just kind of roughly eyeball it for now and follow along. This is the first time we're doing it through Zoom, so we will next year try and streamline it a little bit better and have something for you guys so you can follow along a little bit easier. So apologize for that for this year. Okay, so we're going to get started here. Thanks everyone for coming out and everyone who joined online. Much appreciated. Face-to-face meeting once again. These things are coming back online, so it's nice to be able to actually meet everyone and see everyone. So we have quite a group in the room here, probably about 15 or 16 of us, so that's great. So I'm Kevin Usher. If I haven't met you before, please come and introduce yourself afterwards. And I work with Agriculture and Agri-Food Canada and collaborate with the Wine Grape Council quite a bit. And we've been putting this lab proficiency testing program on now for, I don't even know how long, maybe 10 years. Yeah, but what is that, 7, 8, 9 years? So it's been growing. We're up to about 50 participants right now, and we started, I think, around 20 or maybe 25 or something in the beginning. If you like the program, please share it around with other people. We want as many to participate as possible, and the more we have, the better the information we get back. And so I'm a biochemist, so that's kind of why I'm involved. So I do the stats and the graphing, and often I run the different analysis myself. I didn't this year just because of time, but I always find it very interesting for myself as well. And I got all the fancy instruments, where I rank in terms of everyone else too. So before we get started, I wanted to thank the BC Beverage Technology Access Center, which is here at Okanagan College, for hosting this in this venue, which is great. And supplying the audio, visual, and everything like that. They're also participating in the program here. If you don't know about the BC BTAC, look it up online. It's a great resource for the beverage industry in British Columbia. Also like to thank the Wine Grape Council and for putting this on. I think it's a really great program, and of course all of you for participating. So what I'm going to do is just go through how I've laid out this presentation. And for those of you who've done this in the past, it's pretty much exactly the same as always. So feel free to sleep through some of it if you want. The graphs tell us bits of information about where maybe we can make improvements or not, and also gives us an idea as an industry where we're at in terms of our labs. And we have all different levels of labs, different kinds, commercial labs, you know, just the general wine lab that winery lab might just do a couple types of analysis. So not everyone does every analysis on here. So you might see the amount of data, you know, growing or shrinking depending what it is. Please ask questions along the way if you want. We'll also have a question period afterwards. What else? I think that's about it. So we'll get started. And so you can see the screens here. The handouts I gave you isn't what's identical to the screen up here because I cut out so I didn't have to print so much paper. So you have all the data, and you can follow along a little easier with the handouts I prepared. But I will be emailing out to everyone this presentation that I'm showing here, along with the codes, your individual codes. So, and we use the codes just to keep confidentiality between labs. This year we did have a new feature where labs could identify if they wanted their name put on the presentation or the report. And so you'll see in the list of codes, every once in a while, there'll be an acronym or something like that. So we have 6 labs that identified as wanting to participate in that side of the program. And so we're very thankful for that as well, because it's just nice to kind of gauge, you know, against, well, say like ETS or Okanagan Wine Lab. We had a few other ones, Corslet, Shaberton, who else you'll see on there. There's 6 altogether. So let's get started. Let's see here. Okay, so the whole goal of this is to try and bring the industry's lab testing together so we can be more accurate and precise and really help to use labs to boost quality of wine. So really, when we go through these, you're going to see outliers and that sort of thing, and that's fine. There's always going to be, because the way stats are done, you know, the closer and closer you get to the real point, the tighter the stats come, but there's always people on the edges. So if you find yourself there, don't stress out. It's okay. You know, it happens to everyone. And it could be for many different reasons, from maybe your equipment's not working to someone entering, you know, the wrong numbers in the reporting. Not mentioning any names, Nick. Nick had some wild values, and I called him up and said, "Is this right?" Like, they were all over the place on this one analysis, and he says, "Oh, I think I put them in. I put the red one in the white and the white in the red one. I switched them, and it was just fine after that." So it could be anything at all. And so if you're having trouble figuring out what the issue might be, you can come and talk to me or phone me or whatever anytime you want, and I can help you work through it, and even help you with, say, your pH meters acting up or something. We can compare on different samples like pH meters or whatever, just to try and help out. So try and use this as a resource. And I think other people in this community here would also help out. Okay, so let's get going. Okay, so the first style of graph is this scatter plot here, where we have all these data points in the middle. So each data point is on the left axis here, this is the white pH value. And on the bottom axis is the red pH value. And the point is the combination of those two for each lab. And so these ellipses here, these ovals, these are the statistics. So the red one is it's called a 95% interval, and then the outside ring here, the blue one, I think it is a 99%. So you want your data to be inside that red ellipse. If it's falling on the outside, it means that there's a 95% chance that your value is not accurate, essentially. Or the other way, more positive way to put it, if you're inside the ellipse, there's 95% probability that your result is accurate. So even though there's a big scatter, it means that any one of these points is a 95% chance that it's actual the real value. So what we want to do is eliminate any of these, or find out which ones are falling outside of the 95% range and figure out what the issues are. And this particular graph shows both systematic variations, or inconsistencies, and I'll explain that. So if you see your data falling in this first quadrant or this third quadrant, like these little green dots here, that indicates a systematic variation. So what that means essentially is there's a problem in your system somewhere, or there could be. It's not automatic, but basically it'd be like your pH meter is always reading high. So you can see, say up in quadrant 3, this green dot here, it's always high with the red pH and the white pH. If it's in quadrant 2 or 4, it means there's like an inconsistency in the system. So it means like sometimes it measures okay, sometimes it doesn't. Like it's odd. So that often could be a human error. So in the analysis or data entry or something like that. It could be the instrument, just maybe there's a loose cable or something. Sometimes it works, sometimes it doesn't. And I know pH meters are finicky that way. They sometimes, like my pH meter, if I go close to the pH probe cable, when I move my hand in and out, the pH changes because it's not shielded properly. and that's a problem. So it could be simple like that. So depending on where this lies, it can indicate what type of issues you might want to look at. So I show this graph, and then when the second thing I do with this is eliminate all of these values that are outside that 95% oval and create a second graph. So basically all it's doing is just kind of shrinking it down a little bit more. And then some more will pop outside. So it's just an example of how close you are to that outside edge. And the reason I do that is sometimes you think you're close, but just the way the stats work, you're still fairly stable inside that 95%. So you'll see examples of that later. The next thing we should be looking for is precision and accuracy in our measurements, and those are two very different things. So with precision, this means basically that things are very reproducible and they're repeatable. So for example, these black dots here, these black dots are all very precise. So that analysis is precise, but it's not accurate. These red dots here, they're accurate because they're close to the center. So the center is the mean value. Sorry, I didn't say that. The mean value for this analysis. So these are fairly accurate, but it's not precise. So what we want is a combination of the two, both accuracy and precision. And so in this type of a group, what we're looking for is everyone to be getting closer and closer to that mean value, which is, it's not the true value, but it's as close as you can get to the true value. And so that's kind of the goal here. So if you're doing, say, you have some wine and you do 3 analysis on it and they're all over the place, you need to work on your precision a little bit better. And so it's just important to know this, the terminology here. And then we have these kind of graphs, which are ranked graphs. So they're ranked from lowest to highest. The numbers on the bottom, they're just the ranking numbers. So they don't really mean anything except for the position in the graph. And then on the y-axis on the left is the analysis that's done. So in this case, it's pH. In this graph here, I put, so the top one's red wine, the bottom one's white wine, so it'll be consistent throughout. I put the average pH, and then this plus or minus 0.13 is the confidence interval. So that's, if you go 3.57 plus 0.13, that means it'll be If you're outside of that, you're outside that 95% confidence level. So how we get that is calculating standard deviation. So this line's one time, and the 95% confidence interval is estimated at 2 times the standard deviation. So for all the graphs, just like this bottom one here, you'll see this red line, which is that 95% level, and the black line, which is the mean. On the left, we have all the codes. So each lab will have their individual code unless they're identified where their name will be here. And the red are the values that fall outside that 95% confidence level. The green are the average value. If there is no actual number that's the average that some labs have hit, I'll just put a green line where it should be. And down the bottom, we have this little tiny table with the average and then the 95% confidence level numbers sitting there. And then we have the legend at the bottom of each graph, which is the type of analysis that's been done. So in this case, we have a pH meter, we have FOSS, which is a spectrophotometric method, if you don't know, and then other, which can be another type of analysis, or they just didn't identify what it was when they sent the data. Okay, so onto the results. So the first set here is the, whoops, there, it should be here. So we have, and I'm going to go through these pretty quick because this is something you're going to have to sit down and look at, but I'll just point out some of the trends that I see going on here. One of the things throughout all of these years that we've done this is the data is getting tighter and tighter, and I would like to show that somehow. So that's something I'll work on. But it's just we're getting better and better at doing these analysis, and I think people are becoming more and more aware of how important some of these things are, and also people are doing more different types. So it used to be most people only did maybe 3 or 4 analysis. Now they're doing 5 or 6 or 8 of these. So it's a really good sign. Here, so we have these ellipses look fairly normal. We have a few outliers. So you can see in the top one, we have some that are outside these ellipses. I've removed them on the bottom one. And actually this one, I made a note. I think I messed up because this point is still out here. I will fix that in the final report. But if that was gone, it would probably shrink and maybe include one of these other ones. So that's kind of how that style works. Yeah, we really don't have many outliers on this, so that's good. We can see here the different types of analysis, and like it's interesting for the red wine, the FOSS system seems to measure a bit higher than the pH meter, whereas in the white, it seems consistent throughout. And I've used FOSS before, and just as a note, red wines can have an effect on it because it's like a spectrophotometer basically, but it's the wavelengths go really, really high. And so I think the interference because of the red can cause a problem, but sometimes. But
decolorize, would that help or would that mess it up?
I don't know. Like it's something about, I don't know if it's just that or maybe because it's got lots of tannins or what it is, but usually often the reds will measure different than whites for certain analysis. So you'll see that throughout here. So we've been tracking FOSS, just so you know, for a number of years now, and it's been really interesting. So the analysis has been improving. They're always within the ballpark. They're not, off in left field somewhere. So the system does work. Just some analysis that works better than others, and you'll be able to see that through here. Oh yeah, you guys don't have this graph, but this is just the table of the different methods used, the average values, and then the number of labs that did that type of method. So you'll see that when I send the report out. Oops. Okay, titratable acidity. again, you can see that this is less oval, so the values are actually, they're getting a little bit tighter. When I take a couple of these out, they're outside of the 95%. You know, this is a good example. You can see a few more pop out, and you could do that forever until there's none left. So, but it's just an example where, you know, where your data may lie. So this is interesting because it's like it seems to get more oval when you take some of these out, or more round, sorry. And it just shows, and the reason for that is there's more in these the top left and bottom right quadrants. And so it kind of spreads the shape out a little bit more, which is more indicative of like those inconsistencies rather than instrumental issues. Okay, here's the rank graph for titratable acidity. And an example here, we got, you know, a pretty low outlier here. So this is exactly why we want to do this type of program. So whoever has that, I hope, you know, they'll look at their information, but also get a hold of someone to help out, or you know, if their instrument's not working, then that's really important to know. So, but you can notice, like, if you take that one out, this data is actually, it's pretty tight, it's pretty decent. Like, so for the white wines here, we're going from roughly 5.3 to 6.1, which it may seem like a big spread, but for this many data points, this many labs, and this many people doing it, it's actually not too bad. Okay, so there's the different analysis. Most people use like the traditional methods still for doing these. Here's the volatile acidity. Once again, very few outliers, which is good. This can be a tough one. This is also one where the analysis, different types of analysis give you very different results. We can see here that the cache still gives higher levels in general than, say, FOSS, whereas like the SPEC enzyme method kind of falls in the middle there somewhere. And we can see there's at least 4 different methods used here. If we look at alcohol, we can see these ellipses are pretty tight here. The variability, like this inconsistent variability, is actually it's quite small. So it's more to do with probably the analytical methods that are being used. So when we look at that, again, we can see some differences here where FOSS tends to read a bit higher. The distillation density is kind of that, and the ebullirometer measure kind of in the middle, or in terms of the ebullirometer, a little bit low. And I'm not sure what the other is. I don't know if anyone uses GC for doing this. Yeah, you do. So maybe that's that might be in there as well. So GC is usually one of the most accurate methods, but more difficult to do, of course, and expensive. Okay, so these graphs with the reducing sugar, these ones are, yeah, they're a little weird because none of the numbers go below 0. So the stats aren't really represented well here with this graph. So that's why it's circular shape. There's nothing down in this bottom end here for the stats to use. So I put these in here, but they're not, I wouldn't put too much faith in these ones in particular, just because of that. And we'll see that with malate as well. So reducing sugar is often a difficult one. Lots of different methods. And this one here, the method really makes a difference, particularly if you're doing comparing an enzyme method versus most of the other methods. And the reason is because the enzyme method targets 6-carbon sugars, or fermentable sugars essentially, whereas the other methods include the 5-carbon sugars. So the other methods are often higher than the spec enzyme method. So you can see that in the red wine. So these green dots are the enzyme methods, and you see almost everything else is up higher, and that's probably the reason why. And yeah, but you know, I have to say, in this white wine, anyways, all the other methods are hanging in there pretty good, except the Reblade method always seems to measure high on residual sugar or reducing sugar. Okay, SO2, another difficult one. Here's the ellipses. There's nothing too special going on there. And yeah, there's nothing really too outstanding on here. Phos does not perform well with sulfur, so that's why you don't see, well, you only see one there. And actually, I was surprised it was hanging in there, but it's good. Yeah, aeration oxidation is obviously the main method here in the blue, and the spread is fairly high in the red wine, anyways. So, well, it's not huge, but I mean, not too bad. I don't see anything really strange about this graph, though. So, and total SO2. Whoops. We do have a big spread in the upper levels of the total SO2 here. And again, you know, the Ripper method, aeration oxidation, they seem to be, you know, fairly well distributed throughout. And let's see, I think malate's last. Yep. And malate's this other weird one where for these graphs, makes the graphs weird. So the numbers don't go below 0. So it makes these graphs really oval. And if you're wondering why this bottom one is looks backwards, it's just because the white values are higher than the red values. So it's just flip the graph backwards. So, but fairly normal. The white probably didn't go through ML, so understandable, it's higher. And we do have a couple pretty big outliers on these ones here. So again, this one was strange because in the white wines, the Phos measured high on everything, and then the red, it measured low on everything. So I'm not sure what's going on there. I always find it's kind of like a black box. You put your stuff in and see what comes out. You're not sure what's working in there. And that's it. And then the cold stability, which I'm just going to pass over to Nick. I don't do this analysis. One of these is ETS. And I can't remember which one it is. It might be this low one, because I think they use this slightly different method than what we did, but I'm not sure.
All right. Thanks, Kevin. So yeah, I'm Nick Dursek from Okanagan Wine Lab. Been with the committee since 2017. We just added the cold stability a couple of years ago, just to add another analysis in there to kind of help people kind of zone in on it. I mean, the numbers are looking better, I think. It's just kind of hard. I mean, for me, I was really trying to make sure that everyone's doing the same method. When I was talking to other independent labs, I found that some people were only running it for 15 minutes versus me running it for half an hour, or adding different amounts of KHT, which can also affect how it drops. And there can be a few things that can kind of get in the way if your temperatures are fluctuating too much when you're running it. Try to make sure I don't have a change of more than like a half degree Celsius. So it's important to try to keep it as consistent as possible. Also, when you're starting, you want to make sure that your starting point is stable before you start the test. One variant I've found, when you see low values, not saying that that's necessarily it. Sometimes you can get air bubbles in your probe, which will cause some issues with the reading. I use a little bit of anti-foam when I see that happen, and that seems to kind of clear it out, and then you don't have that issue. If you're running your cold stabs and you're not seeing numbers, in a white, usually they're in that 1200 to 1500 range, and reds tend to be a little bit more in the the 2000 range for starting and stopping. So if you're not seeing that, if you're seeing stuff in the 400s or 200s, or it's bouncing around a lot, you probably have some air bubbles in there that you want to kind of get rid of. Yeah, it's interesting for me to kind of see such variance in the microseisms, because you would think they would all be consistent. That could also just be issues with the standard. Maybe if you're using a different one, or maybe if it's just old and it's just not accurate. So that could, when you're calibrating your cold stability, that might cause a difference. So yeah, I don't know. Every year we kind of see what's going on with it. But I mean, that's kind of been the main thing why I wanted to kind of see where other people's numbers were, to just make sure I was on point. So yeah, I don't know. Is there any questions on cold stability or the numbers or the methods that we kind of chose? I know last year some people were kind of curious about different methods and why we chose the one that we did, versus yeah. So I don't know. That was why I wanted to do it, because I wanted to try to get us all doing it the same, so that our numbers would be more similar, instead of running them different times or different KHT. I mean, obviously you're going to get a different number, a lower number if you're only running it for 15 minutes versus half an hour, or if someone says 5% is stable versus 3% is stable. I've always gone more on the stricter side, being an outside lab. Not that I want people to fail. I just don't want there to be an issue, and they come back and say, well, you said it was stable at 5% when, and then they had an issue. So yeah, it all just kind of comes down to the winemaker at that point. But I've always really tried to put them through the ringer and, crash it hard and do it for a long time, just to make sure that they're stable. So anyway, that's what I've gotten from running them over the years, is just do it longer, and just to make sure that they're stable, instead of doing a short run on it. So any questions?
I was just gonna say too, like every year the wine we get, we don't really know. We get it from a commercial winery, and get it unlabeled, and we don't know really any of the properties of the wines. And every once in a while, one of the wines throws us a complete curveball. We don't know until all the data comes in. Remember one year,
that
residual
sugar,
on
yeah,
the red or
weird.
something was really high, or like there
wasn't reading
what's
properly.
going on.
Yeah.
This year, the wines seem pretty consistent, red and white both, and I think here with the cold stability, it shows that too. Like they were both pretty even, it seems. So.
Yeah. All right. So I guess we can pass it on to Florencia.
Yeah,
Any
if
other
you wanna-
questions, or if anyone had any questions about
just-
some of the other numbers there?
Yeah, so this will be at the end of the presentation, just
Okay.
with some contact info. If you guys have any input at all, it could be anything with the program that you'd like to see in the program change, something you didn't like, something you like, just shoot us a message, and we're always looking to try and improve. So, and yeah, that's all I have for this. So if you want to introduce
Florencia?
and do we need the presentation on that?
Yeah.
Yeah, so I'll work on that.
Okay. So we have Florencia here from Enardis. She participated in the Lab Proficiency with us, and she also has a product for tartrate stability. So she the Zenith. So she's going to talk a little bit about that. And yeah, I'll pass it over to her.
Let me know when you're ready.
Yeah, I just,
Okay, so my name is Florencia. I work for Artis USA, manage the lab there, and in the past we used to do something similar to what you guys are doing here, but now we're focusing on helping clients, and we're not a commercial lab anymore. So we basically help clients use our products and understand the safety limits to make sure that when they apply our products, their wines are stable and safe, and that they actually experience improvement in their wines.
yeah, almost done.
Okay, perfect. So. Should I pass it there?
No, I got it
You
here.
got it.
Let's see.
Okay. I'll tell you next slide. So
Yeah.
basically, I'm here to present about Zenith. Zenith, it's a revolution in the market. It's been a product that it's a relatively young product. It's for tartrate stabilization. And it requires for winemakers to be on top of analysis before application. So that's why my
Just
where
use
I'm
the
here.
mouse or the keypad.
Okay, just
If you click it or roll the.
okay. So these are some of the topics that we're gonna talk about. What is tartaric instability? Parameters influencing tartaric instability. We're gonna move on to Zenith, and then we're gonna talk about the main characteristics of the product. How do we prepare the wine for Zenith? And then the specific analysis that we need to run before applying Zenith and how we need to run them. Okay, so what is tartaric instability? Tartaric instability is due to the content of tartaric acid in the grapes and later on in the wine. Is the most abundant acid in wine, and it's insoluble when bonded with calcium and potassium. It forms different salts. One of them is potassium bitartrate, which is the goal of using Zenith, being able to avoid crystallization. The solubility in water, it's relatively high of potassium bitartrate, so we can see that when there is no alcohol, the solubility is 5.7 grams per liter. However, once there is alcohol in the wine at 12%, we can see that solubility dropping by a lot, so 2.77 grams per liter. So as a conclusion, we know that KHT is more soluble in must than in wine. Therefore, the more alcohol we have, the less solubility we'll have. That's why it's important to consider that. Okay, so what are the parameters influencing tartaric instability? We have promoters and we have inhibitors. Promoters are those substances or conditions that will make crystallization occur faster or to happen once the wine is in bottle. So one of them obviously is the concentration of tartaric acid. The second one will be concentration of cations like calcium and potassium. Then percentage of alcohol, like I said, the more alcohol we have, the less solubility we'll have. Low temperature, UV radiation, filtration because once we filter the wine, we will remove some of the inhibitors that we have there. Crystallization nuclei, which will fasten up the reaction, and agitation will increase the probability of crystal formation. What are those substances that can inhibit this crystallization. So we have low pH and total acidity. Natural protected colloids, we have found out that manoproteins are very effective at protecting from crystallization. Rhabdogalacturonans too, those are also very effective as protected colloids. Some other polysaccharides, tannins, proteins, and of course fining agents like bentonite, PVPP, carbon, gelatin. So moving on to CNES. What is CNES? So CNES is potassium polyaspartate. Potassium polyaspartate is a polyamino acid produced from L-aspartic acid, which is an amino acid that's present in grapes. So it's not an external source. It's part of the nature of the grapes, and it's in different concentrations depending on the varietal. What CNES does, it inhibits the size growth of potassium bitartrate crystals, preventing crystal precipitation. So the main difference between this method and traditional cold stability is that this is an additive method where we're adding into solution a product, a colloid, while the other method is basically taking out of solution potassium. Because we're adding a new colloid, that's why we need to be very careful with the 16 nature on the wine. So, CNES Uno is very effective, fast, easy to use. It's a great tool for stabilization of potassium bitartrate in wine. It's able to ensure long-lasting stability, even in wines with a high level of tartaric instability. Therefore, CNES Uno can easily replace stabilization with cold or other physical treatments. It's very important to consider the long-lasting stability of the product because there are some other colloidal methods like metatartaric acid that are very effective at cold stability, but over time that substance gets hydrolyzed with high temperature. So it is very important to consider that CNES will guarantee stability over time in the wines. It does not affect sensory quality, filtrability of the wine. Its liquid form allows easy and quick use, and like I said, is high temperature resistant. So how do we prepare the wine for CNES? This is basically a chart that shows the flow of how we should get ready to add CNES to our wine. So 6 to 8 weeks before bottling, we should start doing blending, acid adjustments, fining. Then 4 to 6 weeks prior for bottling, we should start checking protein stability. By that, we should do some bentonite fining trials to understand the level of bentonite that we need to add to our wine to ensure that the wine is protein stable. Then, after the wine is protein stable, we'll do a CNES panel, and then we are ready to use CNES. I'll explain every step in detail. Okay. So why is it important for us to remove unstable proteins? As we know, grapes have all kinds of proteins in there. Some of them are very stable. Some of them are not. Some of them are very soluble and unstable. Those are the kind of proteins that might create a problem later on, throwing a haze. So because we're adding a colloid to wine, we want to make sure that those proteins that are a risk, not only for colloidal stabilization, but even for traditional methods, they are a risk to the wine. So we want to make sure we remove them. Those proteins are mostly thaumatin and chitinases, between 20 and 32 kilodaltons. So after we do the bentonite fining trial, we will determine the amount of bentonite that we need to add. We will prepare it at the cellar. We will add it. And then after the bentonite is added, it's very important that we check. We take another sample and we check protein stability again. Once we ensure that protein is stable in the wine, we are ready to start working with our CNET panel. A CNET panel, like I said, is a set of analysis required to ensure that the wine is compatible with CNET. This panel ensures that CNET will sufficiently stabilize a wine for titrates and will not negatively interact with wine proteins. So how does the CNET panel look? Our CNET panel is divided into 2 steps. One is protein stability check, which consists of a heat test, which is evaluating the wine as it is. Colloid test, which is the same test as the heat test, but adding CNET to the rate of addition that is going to be added at the winery, which is always a maximum dose rate. We don't do bench trials with CNET. We just always go for the safe dose of application, 100 mL per hectoliter. And then after protein stability is checked, we move on to tartaric stability. For tartaric stability, we work with 2 different tests, conductivity and cold flow test, and I'll explain those in detail. Protein stability testing in the lab. Well, after checking, it looks like we do very similar methodology, but basically we filter 30 mL of wine through a 0.45 micron filter of cellulose ester. Then we pour the wine into a labeled turbidity tube. We place it into a heat bath for 2 hours at 80 Celsius. After those 2 hours, we remove it. We place it in a fridge between 0 and 4 Celsius. That will allow coagulation to happen. And then the final hour, we take it out of the fridge, we put it in a countertop, and that will allow for coagulation to happen. Right after that, we measure NTUs level. As you can see, our NTUs level for final results are very strict, but the reason for that is because we have found out that testing suggested by the books are based on traditional winemaking. This is a relatively new way of winemaking by adding colloids. So we want to ensure that there will be safety when applying colloids for tartaric stability. Colloid stability test, as I said, is the same test but adding CNET. Tartaric stability. So we have 2 different tests that we run for tartaric stability. We run our conductivity. Conductivity can be run in the check stab that most of the wineries have, and also tartar check. Tartar check is our preferred instrument, just because all the Nardes branches, we try to work with the same instrumentation. But basically, like Nick explained, it's very important that the test gets run for 30 minutes at 0 Celsius using micronized KHT. The KHT used needs to be lab grade to ensure that the reaction will happen completely. And the way we do this test is we run the test in a control sample, then we dose it with CNET, and then we rerun it. And then these are the parameters. So 3% or less of conductivity change, that's what we consider safe. I know that there are some wineries that consider 5%, but we try to go with safety always, safety levels. Cold flow test. So our cold flow test represents the best way to determine if a sample is cold stable under real life conditions that the wine might be exposed to. So cold temperatures, shipping, selling the wine to northern countries. Well, here we're very north, but being from California, we try to expose the wines to those conditions. So what this does consist of is basically filtering 100 ml of the sample. We place it in a cone. I actually brought the cone so I can show you later. The cones are graduated to 100 mLs, and we have one that represents the control sample and one that is treated with zenith. Then we place that in the freezer for 6 days at -4 Celsius. After those 6 days, we take them out. We allow them to get to room temperature, and then we check them visually. This is how they look after we pull them out. So the control sample usually gets crystals on the bottom. And after we treat the wines with zenith, this is how it looks. So that's pretty much we run our zenith panels in-house. And yeah, and so after the zenith panel is been done and that we have checked that the wine is protein stable, it will become tartaric stable after application, then we're good to go. And then zenith should be added right before bottling. It's a product that's completely filterable, so it shouldn't clog the filters. And it will ensure stability through time. It means a lot of energy savings. And of course, it means less labor at the winery. So all this testing has been proven and run through the years. So our goal is to share with people that are willing to use zenith, so they are safe when they apply it to their wines. Questions?
Does it work just as well with calcium tartrates?
No.
Just potassium?
Just potassium bitartrates, yes. Yeah. Any questions?
Are there any sensory effects to the wine?
No, it's actually wonderful. No, it respects structure. It respects color. It does not clog filters. That's the main difference between zenith and CMC. CMC is a great colloidal stabilizer, but it reacts with color material. Well, zenith does not interfere at all. So, yeah. Any other questions?
Is there a shelf life on this product?
It usually lasts, if I remember correctly, I think it lasts for like 2 years. But yeah, 2 years, more or less. Usually what I do in the lab, if I have a client that has a tote of zenith that's been sitting there for a year, I run a few analyses and see if we can extend the shelf life, and we can do that for some customers. But the average shelf life is about 2 years.
Is it manufactured organically?
For organic wines?
Yeah.
No, it's not approved yet. Not approved yet. Any other questions?
Hey, I think you mentioned it's 100 milliliters per hectoliter.
Yes.
Is that a direct addition?
Yes.
So no water addition?
Nothing. It's liquid. So it's just like you dump it, and then you make sure it's very well mixed. That's critical. You need to ensure that the wine is very well mixed with the product, and then you're good to go. Mm-hmm. Any other questions? I can find out for you. Okay. Sorry, it's not my strength, prices.
Well, thanks for that.
Of course.
All right, well, I just want to say thank you for everybody for coming, for your participation this year, everybody that joined for the in-person presentation and everybody that joined online as well. For those here in person, we have some wine and charcuterie to bring out, so if you could stick around for a little while, that would be great. The theme is tightrope and soul barrel. That's what we brought with us. And I just want to say a big thank you to Kevin Usher again this year for all his work that he puts into this program.
Very welcome.
Yeah, and again to the BCWGC and the subcommittee that works towards putting this together every year.
Thank you, Allison.
Absolutely.
So yeah, and just if anyone doesn't receive results by Monday, get a hold of me because I'm going to send them out by tomorrow at the latest. So if I missed you for some reason, but I think I'm pretty solid on it. I've done it enough times. Great. Thank you very much, you guys. And people online, I'm going to disconnect now. So thanks for attending online.